Amir Samoiloff is the CEO at SIGA OT Solutions. Joe Weiss is a managing partner at Applied Control Solutions and is a pioneer and legend in the ICS security community. Please welcome Amir and Joe to the S4 main stage.
First of all, I wanted to thank Dale for inviting us. This is my first time at S4. I actually started the ICS Cybersecurity Conference in 2002. And the concept that there could be over 500 people at a control system cybersecurity conference to me is phenomenal and mind-boggling. I don't know how many of you were here last year. This is kind of a shameless plug. But Richard Clark was here last year as the keynote, talking about his new book, Finding Cassandras to Stop Catastrophes. And there is one chapter in the book that's on cyber, chapter 14, and the chapter is about me. I've never had anybody do that before, and so that's kind of a kick. I also wanted to point out a couple of things before we start. And this happens because when I don't go first, I get a chance to listen to everybody else. One of the things that was brought up earlier was the concept of vulnerability assessments. Vulnerability assessments are gap analyses from how far away you are from where you think you are with security. The whole point of what we're talking about are, quote unquote, the level 0, level 1 devices and their device networks. There is no security or authentication at this level, which means there is an infinite gap between security and what these devices are. What also means there is no vulnerability assessment methodology when you get to this level. It's an entirely different concept. The other point is, you keep hearing about the term situational awareness. It's really, truly difficult to have situational awareness if you can't trust what you measure. And that's the starting point of everything. So with that, and also I will apologize, but I always have notes and some type of prop that I bring with me. So with that, I want to start going through, in a sense, what the issues are, why we're doing them, and then I'm going to have Amir go through some actual real cases of using monitoring to detect electrical characteristics all the way down at the physics layer. Because everything you've seen or heard up until now, and what you'll hear after us, is all necessary. None of it is sufficient. This is the part that needs to be added in order to have a complete solution from beginning to end for control systems. I won't even use the word industrial, because this includes building management, it includes medical, automotive, defense. I want to get away from the term industrial. It's much too confining. The first slide I want to get across is, I'm sure people have heard about the Lion Air crash. That was the crash of the brand new Boeing 737 in Indonesia. And what it was bad sensors. People are very concerned about protecting the PLC or the controllers. In this case, the controllers did exactly what the bad sensors told it to do, which was to point the nose down and fly that plane into the ocean. And the controllers had no way of knowing that that was the wrong data. And because the automation system was not turned off, it overrode the pilot's attempt to correct where those controllers were taking them, and 189 people died. And for those of you who are my generation or maybe the previous, what I've got there is, if you remember 2001, Space Odyssey, this is HAL. This is the computer overriding the person. Now, the next slide, and we're going to go into precisely why I'm saying that there's a hole in the Plum Island test, which was the DARPA test. And there's a hole in the situational awareness that was behind that. What happened was they were using a diesel generator as black start. In other words, to provide the initial, power in which to bring the grid up. If that diesel doesn't start, there is no grid. And everything you saw after is meaningless. And what we're going to show, and especially through the coming slides in a real case history, is how sensors could have prevented that generator from even starting up, be it manual or automatic. What's happening here is our big equipment, not even big equipment, I have a shredder at home that's gone through this. You have sensors in there as effectively safety interlocks. If something gets too hot, if the voltage gets too high, too low, whatever, it will shut off the equipment so you don't damage the equipment. You can't bypass these sensors. These are part of the design of the equipment. And there's effectively almost no forensics there today. If you change the set point on those sensors and you set it low, you will shut off the equipment every time you try and start it up. If you set it too high, you no longer have any protection. Like I say, we have a little shredder at home. When we put too much paper through it, that temperature sensor will shut that shredder off. And we can't use it again until the temperature goes down, no matter what we do. Now, all of this was done for the good guys. Whoever thought a bad guy would want to take advantage of something like this? And this is not something you're going to find from networks. This is my little techie slide, and it's why we're here and what's missing. When you go all the way over to, let me see the pointer, on this side of, oops, I should do this. They told me and I didn't listen. This is pre-Stuxnet, what people were looking at, basically the HMI and the IP networks. Following Stuxnet, all of a sudden, programmable logic controllers became a very big deal. And we're now very worried that somebody could change firmware logic, etc. What this presentation is about is what time forgot. It's these things, these 1970s, 80s, and 90s hardware equipment that when you see these boxes, that's the electronics that allows for remote access. There's firmware. It's what makes 1970s or 80s or 90s 2018, 19, or 20. And that's where we have no cybersecurity, no authentication, no cyber logging, and yet this is the input or end actuation of everything you do here. And we're also talking about the lowest level sensor networks. Serial Modbus, HART, wireless HART, Profibus, Foundation Field Bus. This is not where you're looking up above at things like, IP Modbus or things like that. How did we get here? Why are we where we are? Prior to 9/11, the people that owned and ran the equipment, the turbine engineers, substation engineers, owned everything. And back then, it was a business problem. It was not national security. Because you can't make things if this equipment doesn't work. Well, following 9/11, cyber became national security. and it was yanked away from the operational groups and given to IT, or now you can call it OT. But the unintentional consequence of that was cyber became the network. This is the necessary for all of you, but the lack of sufficiency. Because what happened was those sensors, analyzers, power supplies, you name it, were considered to be engineering systems. And they, quote unquote, fell off the turnip truck. To this day, there is no security requirements for these systems. Not only am I the managing director of 99, I chaired a special task group to analyze all of the 62443s to ask, are they addressing these legacy devices? And the answer is no. There are no standards anywhere that are addressing these lowest level devices for security. And what's more, I'm getting involved now with the safety standards, because the safety standards aren't addressing the significant issues associated with these sensors and actuators. So this isn't just within ISA 99, this is now also ISA 84. And there's also, for what it's worth, I'm giving a joint presentation at an American Nuclear Society conference, because it's also a whole in nuclear plant cybersecurity. Now, what happened many, many, many years ago, and why we're worried about all of this, as an engineer, the way I would look at and know if a sensor is working properly or a process is looking properly is I look at what's called a process noise. It's the wiggling you see, if you will, at the physics layer. And that's essentially what happens when you do vibration monitoring, flow-induced vibration, sensing line, anything that's dealing with the physics of a process. What happened was, in the 80s, late 80s, early 90s, the engineers wanted all of that data to be on a network. The networks weren't robust enough. So the engineers gave up with trying to get this very, 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 resource-consuming data on a network. But in the late 90s, if you will, mid to late 90s, early 2000s, with the advent of Windows and Linux and Unix and, with VAX VMS, I don't care what it is, these systems are slow. They're on the order of, say, 2 to 4 or 5 seconds, which meant that all of this higher frequency noise can't be used by Windows or anything else. So I'm going to go back a slide. What you have here is the serial to Ethernet converter. That's what takes the data that's coming from these devices, which is analog, and going through all kinds of things and then converting them so you can put it on the network. And this is also where, in a sense, you would be bringing things into an asset manager. You heard John Cusimano talk earlier about this is how you can go down directly into the devices. So what's happened is this device has filtered out all of this higher frequency noise, which is what tells us whether things are working or not. It's why it's not possible when you monitor at the network layer to actually know if the sensors or the process is working properly. That's why what you're doing is not sufficient. Now, what we now have the ability to do is take what people may not like me saying, but it's true, an intractable problem when you look at cyber from the network layer and turn it into an engineering problem which is solvable. And it's really making a thing called process anomaly detection, which can be then combined with network anomaly detection. What we're missing is what's going on with the process. Why are we doing ICS if we are not even worried about what's going on with the lights? So what we're looking at is using the ability to monitor the physics of the sensors, which are the eye of the process, in real time. This is ground truth. Networks are not ground truth. Networks take their information from the sensors. What we want to do is be able to monitor the sensors in real time. That's telling you whether the process has a problem. So all of the things you heard about, the CV scoring and whatever, as an engineer, that doesn't mean anything to me. What means everything to me is the process working? That's what you've all left out. That's what needs to be included to make everything sufficient. Now, this is also another really big deal. You've heard all of these discussions about the IT-OT convergence. I believe it's the wrong discussions. The real discussion is what's going on at the process before it becomes a bit or a byte. So the real gap is not, is IT or OT talking? Are the engineers who are not OT? OT is the network. OT is not that turbine, motor, pump, valve, relay. It's getting those people involved. That's what's been left out. And when you start talking about the real control system cybersecurity experts, that's not IT or OT. That's people who actually understand what we're really trying to do. Now, I want to go through this, and then I'm going to turn it over to Amir to talk about real case histories. Actually, I got 2 slides first. But one of the things you heard, again, John Cusimano say, is that through the asset manager or other ways, you can get down all the way into these devices. And you can change things like span, range, damping. I can brick any PLC from the sensors. And there is no way to know what's happening because it's the data that will brick the PLC. Well, what's happening is Yokogawa did a study on a refinery in Japan. And what they found was that 50% of the nuisance alarms were instrument failure or improper ranging. They were assuming they were nuisance alarms. They didn't know. They're assuming they are. This is again going back to we have a hole that we need to fill. This is what I mentioned before. What I worked on years ago, I became an ISA fellow not because of what I was doing with cybersecurity, but what I was doing here with the analysis of the data and trying to understand forensics. I just didn't have modern machine learning or the ability to do things in real time. That's what's changed from 30 years ago to today. I can do things now. This technology allows me to do what I couldn't do before. And by the way, this is physics, and you cannot hack physics. Now, again, this is what I wanted to get across. What's missing in everything we do is the process anomaly side. What we're bringing in is essentially that. And also one other thing, you hear all about predictive maintenance. The sensors aren't just for cybersecurity. The sensors are what you use for not only operations, but all of your maintenance. We need to be able to trust what we measure. That's not being done anywhere today. What is happening today is it is assumed that the sensors are uncompromised, accurate, and authenticated. And they are neither or none of those three. And one other last point. The co-chair of my committee on looking at these level 0, level 1 devices got his doctorate from the Air Force Institute of Technology. His doctoral dissertation was on hacking wired heart process sensors. And the next cohort is going through on doing hacking wireless heart process sensors. And one of the things they've also been able to do, because I had put a blog out about how important it is to monitor and know what's going on with sensor drift, they have been able to hack and maliciously cause sensor drift. You want to know, can you get down to these devices? Yes, you can, and you can hack them. And neither the PLC or the HMI will have any idea, because you've done it before it's a packet. That's where there is no real situational awareness today, because we're not down at the layer low enough. And with that, I want to have Amir take you through some real case histories so you understand this is real and can be done.
We rely on the risk assessment that the customer is doing, and we actually take between 3 to 7% of the total amount of the IOs, and we just tap into it. It's not rip and replace. It's very, very simple tapping. Most of our installation takes us less than 1 working day. And by that, we receive a very, very secure, 100% truly out-of-band solution, because we are not part of the OT. We are not receiving even 1 packet of information from the SCADA system. We just sample and measure electrical signals. In that use case, we hooked into power generation turbine, and the turbine could not ignite, could not start. And they could not understand the exact problem because they could not see the sensors. And the sensors was the problem. And after seeing the exact sensor situation from our system, they could start the turbine in that same evening.
The point that's I'll use this. The point that's so important about this goes directly to the Plum Island test. This was a turbine that wouldn't start. It wouldn't start manually or automatic. The HMI data said that the sensors were good because the HMI data wasn't granular enough. When you started looking all the way down into the bowels of, if you will, the noise, what they found was a bad temperature sensor. That's what prevented that turbine from even starting. You do that from Plum Island, that diesel generator doesn't start, you have no grid. What's important here is to realize this isn't hypothetical. This really occurred. Was this cyber? Not malicious. Could it have been? Sure. But you're talking, here is a major piece of equipment that couldn't even be used.
The next use case is just about you letting, I can show you that we are not just tapping and seeing temperatures and vibration. We also can see a pH measurement, and that's why the solution is so strong. It just see the electrical signals.
Go ahead. Oh, next. Yeah.
That slide, I wanted to show you that actually we are not window dependent. Even if the SCADA system or the HMI doesn't show you or have any problems, our solution can keep on showing and give you the exact situation of your real critical assets.
Yeah. The point here, there's 2 things about this. Again, this is a real case. There's nothing hypothetical or vaporware. While they were doing this testing, the Windows-based HMI went down. Was it hacked? No. Could it have been? Yes. Doesn't matter. This thing kept working even though Windows was down. If you think about Stuxnet, Stuxnet was the man-in-the-middle attack, where they were able to compromise the HMI. Because this is looking at the physics of the sensors. This can't be hacked. There is no way to prevent you from knowing something is actually occurring. And by doing this also, they found a pump problem at another facility they couldn't find any other way. Because again, you've got to look at the physics of the process. And by the way, this is where security, reliability, and safety come together. Not at the network, but at the devices.
Another use case from US customers, you can see the fluctuation and the granularity of the information that we can actually see. This is BMS case study. We also do BMS, and I will turn the microphone to Joe.
Okay, the key outcomes are this. And like I say, we're starting to look at, because the technology exists, and this is not saying it's Sega, it's saying technology exists. Because this exists, we can start looking at what we can or can't require. We've got a hole we've got to fill. The thing about this approach, and again, what they're doing is what engineers were doing 30 years ago. This is essentially back to the future. We just didn't have the level of machine learning then that we have today. And we didn't have the ability to do it in real time. The beauty of this is it learns how different sensors relate to each other. So you can look at things like pressure, level, flow, temperature, and motor speed. They're all related by physics. So when you do the supervised learning, you're understanding how all of these sensors relate to each other regardless of the process, which also gets you away from false negatives and false positives. And it really becomes online sensor or process health monitoring. Again, an input directly into what everybody else is doing. The other big points there is that, again, it's independent of whatever process you want. And it doesn't matter what is going on the network. This is ground truth. And I wanted to end it with one. It was really a funny test case, but why I got so interested in, and also why I had a long discussion with GE about digital ghost. About 10 years ago, we had a dam that failed. It failed because the sensors pulled out from the wall and gave erroneous readings to the SCADA system that turned on pumps until that dam collapsed. What Sega did for me was a demo showing that when the sensor moved, even though the level didn't, the electrical characteristics changed and they could see it. This was allowing you to know when to use all of your tools in your toolboxes. The real bottom line, because we're almost out of time, is we don't know when to use our tools. This is what tells us when.